Good morning, everyone. Welcome to our Nuclear for Net Zero webinar. My name is Scott Milne. I'm Head of Insights at the Energy Systems Catapult, and I've been running our overall Innovating to Net Zero programme here. And the work that you'll hear about today on nuclear is one part of that. So I want to give you a brief overview of the wider programme before handing over to my colleague Mike Middleton to lead the webinar. And then I'll be chairing the Q&A session at the end. So if you'd like to pose any questions for Mike, you'll see a Q&A feature in Teams. And if you drop your questions in there, I'll pick it up and I'll pose as many of them as possible to Mike at the end. So as I say, today's webinar is part of our wider Innovating to Net Zero programme. We launched the main report in March, and it takes a national whole energy system modelling approach to ask, how can we transform power, heat, transport, industry, land use, the entire economy to get to net zero by 2050. And in that report, we explore a couple of scenarios, clockwork and patchwork, one with more emphasis on technological change and the other involving more societal change. Then we commissioned a series of supporting analyses looking at public understanding of net zero, digitalisation for net zero, along with a range of engineering deep dives to focus on the potential of particular technology families, and you'll hear about one of those today. And the Nuclear for Net Zero report is now live on our website, so if you haven't done so already, do visit the ESC website and download a copy. And of course, you can also find all the previous webinars and reports in the series there as well. So once again, if you have any questions during today's session, then please do post them in the Q&A feature. But for now, I'll hand over to Mike Middleton. Thank you.
Thank you also for taking time this morning to listen to this new piece of work about nuclear for net zero. And this content slide here shows the running order that of the material that I'll go through. I plan to speak for about 35 minutes, and as Scott has mentioned, he'll take time at the end for any questions. So be a little bit about the catapult, bit about the approach to the analysis and how we've undertaken this, and make no apologies, this is a deep dive piece of work rather than a very high level overview. We'll talk through the results of the analysis and then conclude really with, so what does this tell us and what does this mean? So just a little bit about the catapult. It's an organisation which is intended to bridge the gap between a number of stakeholders. We have a hub in Birmingham, a hub in Derby with 170 people, and we're sponsored by Innovate UK, and we work as a not-for-profit organisation. One of the things that we look at hard is a whole systems approach, which means joining up sources of energy, breaking down silos between sectors, and also joining up the physical requirements with those things needed to turn that into a modern energy system. Modelling capability is very important to us, and we use various modelling tools to enable industry, government, regulators and investors to better understand cost and benefits of different technologies, which can allow us to understand a transition to UK net zero. One of our tools is known as ESME, this one on the top left of the tool shown on this slide. And this is a tool which was inherited from the Energy Technologies Institute. It's been 10 years in its creation and development. It's been internationally peer reviewed, and its real purpose is as a technology neutral, policy neutral, nth of a kind model. And its intention is through examining multiple scenarios in multiple pathways to look for technologies that may represent development decisions of low or no regret in this transition to a low carbon economy. So it's not a market model, and we don't pretend it is. It's important to therefore understand the purpose of the model and the assumptions that we use. And so the first key message from me, and you'll see I've got a number of these sorted through the presentation, so you don't need to wait to the end to see my conclusions, is we need to be clear that ESME is not a market model. It's technology and policy neutral, and its purpose is for identifying options of low or no regret. And it's a model that runs as a benevolent dictator, launching the right projects at the right time to both decarbonise and look for the lowest cost route to achieving net zero. So moving on to the approach for this analysis then. This analysis has been funded as part of a project delivered by the Energy Systems Catapult that was funded by a grant from Innovate UK. And it was purposed to better understand technologies and pathways to achieve UK net zero. The flagship piece was a project and report launched by Scott and the wider team back in March. That's also available on the website, as Scott has discussed. But there are a number of deep dive engineering analyses, and work package 7 within the Innovate UK project was about nuclear. And so occasionally I may lapse. We're talking about this now as the work package known as Nuclear for Net Zero. Now, what the earlier work did, the flagship project did, is it looked at our previous decarbonisation scenarios, which were modelled to deliver a decarbonisation of 80% compared with historic records. And it looked to stretch the decarbonisation achievable with that existing basket of technologies. But what my colleagues discovered is that there will be a limit to the decarbonisation which could be achieved, at which point the model started to become unstable. So with some stretching of the existing technology data sets, we found a scenario where we could get to a decarbonisation compared with historic levels of up to 96%. And we called this then our further ambition 96 scenario, because it gets most of the way there, but not all the way there. Then on this grid, if you go up one to Tech 100, my colleagues found that by the addition of some more speculative technology solutions involving direct air capture of carbon, more biomass for sequestration, and combining carbon capture and storage with 99% carbon capture rates, we could solve all the way to net zero. And we call that Tech 100 because it's a technology solution. But on the bottom right of this chart, another way of getting it to solve was looking at societal demands. And by changing those societal demands and behaviours through a combination of things such as restricted aviation growth and a changed diet, then that was another scenario that could solve all the way to 100%. And the fourth scenario is this combination of Tech 100 and SOC 100 into the scenario we call best of both, or Bob 100. So we have a combination of scenarios for looking at the achievement of net zero. Now, in most of the analysis that I'm going to show you, we use the Tech 100 scenario. And we looked individually at the new nuclear technologies of Gen 3+, light water, small modular reactors, and Generation 4 nuclear technologies, all tested in isolation to determine their system value. We then went on to a combined assessment where we wheelbarrowed them all in to look for an optimum solution. But throughout the analysis, we occasionally use Further Ambition 96 and Bob 100 to look and test for the resilience of these technologies and the benefits they bring across multiple pathways. And my view is it's a relatively pessimistic approach for nuclear because we're testing nuclear heat supply systems, all of which proven and running today, and the question is taking them to commercialization through either scale up or scale down. So next key message is achieving net zero is hard. You can get a long way there, but it's that last element to 100% which is really challenging. And this analysis suggests that you need speculative technologies or behaviour change or both to get all to the way to UK net zero. So our project approach here was that in our existing ESME model, we already have a range of nuclear technologies, and we were going to replace the previous assumption regarding Generation 4, that it would always be more expensive than existing technology, with a new advanced nuclear technology for flexible cogeneration of power and hydrogen. And this was based on published and accessible reference concept designs in the public domain. And the next step then would be to revise the data sets for these ESME technologies using data from both the ETI nuclear cost drivers study and also contemporary data available in the public domain. We can design and deliver this comprehensive scenario analysis to look for a range of things, including tipping points at which pathways change. We'd also examined towards the end what the analysis really tells us, and it's important to know that remember that ESME is not a market model, and we don't pretend that it delivers a system blueprint for exactly what 2050 should look like. It's about looking for technologies of low or no regret, and we see what this analysis might tell us in that space. So the ESME model is well established, and there's 6 years of knowledge building projects from the ETI that have contributed to the data sets that we use in ESME, from things such as the power plant siting study delivered by Atkins through to the nuclear cost drivers study delivered for the ETI, reported in 2018 by Lucid Catalyst. So the technology change that we made in this new analysis is by putting this new advanced nuclear technology in as a ESME technology. And ESME is actually blind to what particular design it is, what particular reactor variant it might be, because it's actually represented by a set of numbers in a data file. But the way it's represented is we assume it's a higher temperature heat supply, and that it's optimized for cogeneration of both electricity and hydrogen. But it's a flexible plant, and not in fast response, but in a mode consistent with day-ahead planning, when electricity margins are low and prices are high. With day-ahead planning, the plant can shift to full electricity production with no net hydrogen output. And the converse is true when margins are very high and prices are lower. The plant can migrate to full hydrogen production with no net electricity output. And as I say, there are referable concept designs in the public domain which describe this. So it's really important point here that by embracing the learning from the ETI nuclear cost drivers study, I've baked in those cost reductions as inevitable. And failure to move towards those levels of cost reduction could mean net zero with low or no nuclear, which is possible through the analysis that I'll show you. So I won't show you many of these charts, but this is an illustrative output from ESB, which shows how it progresses a decarbonisation of the power sector from historic perspective through to 2050 in a sequence of time slices. So this particular scenario that I'm showing here is further ambition 96. So that's without the speculative technologies. And as you can see, there's a real hard push towards electrification, and the amount of capacity largely from renewables that you can see on the right-hand bar in this chart. This is the matching chart. Instead of grid capacity, this is annual power generation. And you can see in the bar on the right that towards the bottom and middle of the bar on the right, the light blue, mid blue and darker blue are all electricity from wind. And we can see at the first indication that energy from wind is the key technology for decarbonising from power. So I won't show you those transition charts again. I'll try and summarise the results. So this is a chart which on the left shows 3 different scenarios for electrical generation capacity at 2050. And on the right shows 2050 annual electricity generation in terawatt hours. And what I shall use, and some following charts, is a little cheat sheet. And if you see that at the top of these charts, it tells you what the individual runs are. So the run on the left is further ambition 96, run 3A is Tech 100, and run 3B is Bob 100. Now, if I focus on the chart on the right, we can see that there is an enormous quantity of renewables delivering an enormous quantity of power generation in run 3. And this is partly explained because there's little emissions headroom, and to deliver the hydrogen needed for the hydrogen economy, there's a lot of low temperature electrolysis being supplied by this generation figure. As we move to run 3A and the introduction of what we've called the speculative technologies, this creates more emissions headroom, and so there is a lower deployment of renewables. And as you step across to Bob 100, effectively there is a lower level of demand, resulting in a little bit more emissions headroom, and we can see that in the chart on the right. But again, there's a message here in that the blue in this chart is energy from wind, and so it's a key technology. So moving now to looking at a series of scenarios where we have big reactors, Gen 3 plus reactors deployed in their own without deployment of light water small modular reactors or advanced nuclear. And we can see, using the cheat sheet in the middle, we have installed capacity at 2050 at the top, electricity generation at 2050 terawatt hours in the chart at the bottom. And the first 3 scenarios on the left are the ones that I've already showed you. Now, what the rest of the runs show, from run 6 all the way across to the right, is a relatively large deployment of Gen 3 plus nuclear plants, with the exception of run 5. So if we talk about run 5 for a moment, then this is where we've set up an arbitrary cap on the deployment of new nuclear, effectively through a policy cap, and that's where the extent of new nuclear is constrained because there's simply a cap on the amount of deployed. So that if we look across the scenarios to the right, other than the one where there's a cap, there's quite a fulsome deployment of big nuclear across all these scenarios, from Further Ambition 96 to Bob 100, and whether the costs are higher or lower in the sensitivity analyses that we've run. So key message now is energy from wind is the key technology for decarbonising power, but we can see in this analysis already roles for nuclear and multiple applications for carbon capture and storage emission abatement technology. So this is a set of runs now laid out in the same way, but for light water small modular reactors deployed alone without deployment of Gen 3 plus or Gen 4. And in ESME, we have the technology set up so that light water small modular reactors can be deployed for combined heat and power, delivering power to the grid and heat via hot water pipelines into district heating systems. And we can see the no nuclear chart on the left, but when light water small modular reactors are available to ESME as a technology option for decarbonising at low cost, then effectively it's pulling on all the capacity that's permitted in those first 4 runs. The last 3 on the right are where we've increased the deployment rate and the site capacity limit, deployed as electricity only, and the optimization is pulling pretty consistently on that additional capacity. So I mentioned that this particular technology, light water small modular reactors, is set up for combined heat and power, and this is a set of runs. The first 3 on the left are again the no nuclear deployment, and the key point of this chart is it shows that district heating is deployed at scale, whether nuclear is deployed or not, because it's the right choice in dense conurbation areas. But the availability of low cost heat at scale does make a difference, and we can see that in the blue bars further right across the chart. The point here is, in the model, we've only so far enabled light water small modular reactors to do this, but all nuclear technologies are capable of energising district heating systems. The key issue is transporting the heat from the plant to the network. So if district heating is deployed in cities at scale, then heat supply from nuclear can be a very cost-effective option. And what we've set up in the model is that based on their spacing and siting from the learning from the ETI power plant siting study, light water small modular reactors could have shorter connecting pipes to make lower cost connections to hook up with those district heating networks. So I'm looking next at the final analysis of nuclear technology in isolation, and this is for generation 4 cogeneration without the deployment of Gen 3 Plus or light water small modular reactors. So hopefully you'll be used to the chart layout by now. On the left, the bar is the no nuclear run, and on the right we can see salmon pink colour, which represents the deployment of the generation 4 technology. So the first 5 bars after no new nuclear is with a site capacity limit of around 22 gigawatts, and then the next 3 bars are with a raised site capacity limit and rollout rate through to 2050. And at the cost profile, that technology is attractive within the optimization that's undertaken with ESME. But there's a couple of funny things to remark about in this chart. The first one is run 15, where we can see there's a pretty substantial deployment of capacity. So this is run 15, which is the second bar in from the left. But in the bottom, we can see there's virtually no electricity generation. And that's because in Further Ambition 96, emissions headroom is really tight. And in system optimization, in that particular scenario, the majority of the energy from the generation 4 cogeneration plant is diverted into hydrogen production, with electricity production occurring only when margins are tight. But if we transit all the way to the right, there's a run here where there's no electricity deployment and there's no electricity generation. And this is a run which we've set up where the plant's no longer cogeneration, it's hydrogen only. And we've been examining whether it becomes attractive as a hydrogen only plant. Now, for brevity, I won't go into the detail of that and further runs. But the purpose of that analysis, and it's documented in the report, is looking for the tipping point at which Gen 4 no longer is just supplying the hydrogen economy, but the cost point it needs to hit in order to drive the hydrogen economy. So a couple more key messages here. To achieve net zero, hydrogen is a key energy vector, and there are many options for hydrogen production, but relatively few choices for high volume, low cost and low carbon footprint hydrogen. And the analysis suggests that low cost advanced nuclear with higher cycle temperatures could be a combination for higher temperature, higher efficiency hydrogen production. So moving to the last brace of charts here, where we put all 3 new nuclear technologies in combination and a look for how an optimized approach lines up. So this set of charts then is for all nuclear applied in combination, and to help you with the color code, the deep orange at the bottom is legacy. By 2050 we'd anticipate that's just sizable B. Then the orange is big generation 3 plants, the yellow color is light water SMR configured for cogeneration, and the pink above it is advanced nuclear. And there are a few things to just observe across this spread of charts, and one is that blue blob is still there. You know, wind is the key technology for decarbonising power, but we can also see that the salmon pink and the yellow is pretty consistent across all these scenarios, but the one that varies is large Gen 3. And there are a few reasons for this, but it's indicating, particularly in run 26A all the way to the right, that as you in our sensitivity analysis move from our base assumptions to our higher levels of capex for nuclear, the technology for which deployment erodes is large Gen 3 plus, and that's just coming back and indicating this cost sensitivity and importance of cost reduction. I won't dwell on this slide, but this is really just an illustration of, in relative terms, the low cost of lower grade thermal energy from nuclear for energizing district systems in heat networks. If you can transport the heat from the plant to such a network, it's very, very low cost compared with the alternatives, and it's consistently deployed at scale across a range of scenarios. I'll dwell a little bit more time on this chart, which is examining hydrogen supply. So the chart on the left represents consumption of hydrogen at 2050 from the ESME scenarios, and it's across three scenarios, which are Further Ambition 96, Tech 100 and Bob 100. Now, if I start with supply from Further Ambition 96 on the left, as we talked before, emissions headroom is tight. We could see in the light grey that there's a strong pull on hydrogen as a route to decarbonising industry and less use of hydrogen in the next scenario. Of the speculative technologies in Tech 100 and Run 1A, there's a bit more emissions headroom. So there's a bit more hydrogen going into the network, and industry decarbonises using a little less hydrogen and accessing energy from other sources. Run 1B is the Bob 100 scenario, which reflects slightly lower levels of demand. And we can see again, there's less use of hydrogen industry. So if we flip to the charts on the right, these are the corresponding technologies apply. In the run on the left, there's a mixture of steam methane reforming and other technologies with carbon capture and storage at a 95% capture rate. There's also a good slug of low temperature electrolysis. And we've mentioned earlier that the Gen 4 technology gets prioritised towards hydrogen production. Run 1A shows that with the addition of the speculative technologies and carbon capture rates at 99%, that balance changes. So hydrogen from nuclear is still an important component and contribution, but alongside capture and storage. And for the Bob 100 scenario, this is just reflecting a reduced demand. So in ESME, good practice from my colleagues that run these models is to combine a range of deterministic analyses with a probabilistic analysis across 100 simulations in a Monte Carlo approach. And what this chart shows is the results from such a Monte Carlo analysis, and it shows technologies by capacity for electricity generation in 2050. And the data that we've used for nuclear, for all of the new nuclear technologies, we've taken the base value, but applied a spread of -25 to +40%. So it's broader than in our deterministic studies. So there's a few things that come over from this chart, but let me just take a moment to explain how it works. So there are 100 simulations. If we look at the plot on the left, the bottom end of the whisker is the point at which no simulations resulted in a deployment lower than that. At the top of the whisker is the point at which all simulations occurred at a level at that or lower. And the top of the box is the limit of the upper quartile range, and the bottom of the box is the limit of the lower quartile range, and the black line across the middle is the median. So that's how the chart works. And it tells us a few things. First, surprisingly, looking at the technology on the left, wind is the key technology for decarbonising power. But we've seen that already in the deterministic studies. If we look all the way to the right, thermal and carbon capture and storage deployment levels are relatively low for carbon capture and storage applications for power. And that's because in all of these scenarios, CCS applications get prioritised towards hydrogen production and decarbonising particular industries that otherwise would emit carbon dioxide. So CCS deployment is relatively low. Then if we look at the nuclear technologies, second, third and fourth from the left, the optimization really quite likes this nuclear generation 4 technology because most simulations pull on it to the limit of the site capacity, the deployment limit. And similarly for light water small modular reactors, it likes that combination of heat and power. But there's a greater spread for nuclear Gen 3, and that spread, given it's a very high design capacity technology factor, sort of broadly matches the spread for wind. There's a larger spread, but that technology has a lower capacity factor. So we can see again the cost sensitivity of Gen 3 plus and the importance of delivering on those cost reductions to get it to the point of it's a technology in the mix based on merit. But if we look at the deployment levels, you know, the lower level of the box, the 25% quartile limit, you know, that's about 14 gigawatts electric, the bottom of that box. The other chart I'll show you from the Monte Carlo analysis is the one looking at heat supply to heat networks, and this illustrates both, you know, the attractiveness of heat from nuclear if you can transport that heat from the plant to the network, and also the other technologies available in the mix to supply the heat if that low-grade nuclear heat's not available. So another key message here, multiple roles for nuclear in a net zero world: power generation, potentially district heating energisation, and hydrogen production. So moving now to what this analysis might tell us in considering technologies where the potential deployment is low or no regret. So it seems across the spread of analysis that we've looked at that around 14 gigawatts of new nuclear by 2050 could be such a decision of little or no regret, provided that the cost reduction assumptions and construction duration reductions that we've assumed, provided they are delivered in line with the expectations from the ETI nuclear cost drivers study. And such a mix might be made up of Hinkley Point C, which is committed investment, a life extension to Sizewell B, which is expected, and a further intentional programme of around 10 gigawatts of big nuclear plants, which isn't yet committed. But at the same time, launch a stage-gated development programme for light water small modular reactors, and also a generation 4 stage-gated development programme. And the technology for this, which I won't explain why, but it gives indications in the paper, is high temperature gas reactors, largely because of the technology that's closest to commercial deployment, but also the higher temperature process cycle is very attractive. And that suggested approach would then be followed by regular progress reviews from 2020 through to 2030 to support further deployment decisions, not for just nuclear, but across the low carbon energy technology spectrum. But what this analysis suggests is that for large Gen 3, the decision is not when to start, but when to stop. If light water small modular reactors or Gen 4 don't deliver in full on their promise, then this analysis would suggest that you continue building Gen 3 plus. So considering market policy and regulatory issues for nuclear, there is a range of policy issues for further development shown on the left. Accessing affordable capital is really important. There's been a consultation on RAB, but there are also other mechanisms to access lower cost capital. We need to step off an approach of a one-by-one nuclear plant consideration process because it's artificially keeping costs high. We need to stage gate and move forward with technology development programs. We also need to give some further clarity and certainty around developing markets if we're going to access and bring forward private sector investment. And there also needs to be an approach on the strategy for designation of potential sites for nuclear development. What we have in the policy basket at the moment is fine to get us started, but for private sector investment, there will need to be certainty that there's a route to delivering more. So that's policy issues for further development. But on the right, there are also some ongoing issues requiring continued management, but by both government and industry. An issue that regularly comes up in consultation is confidence that progress is being made, both with nuclear decommissioning and associated interim waste management, and an ultimate route for disposal for higher level wastes. An issue of growing importance is going to be the need for the sector to demonstrate its delivery of value for money and a good steward of public and investor funds. And finally, public attitudes and public support continues to be really important, and the sector needs to engage, listen, understand, because seeking to make policy decisions around nuclear deployment in the face of public opinion is an ask too hard for politicians. So my pronouncement key messages here. Policy frameworks for decarbonising space heating and industrial heat are important, and also the market framework for hydrogen supply. The suggested approach from this analysis is Hinkley Point plus a further 10 gigawatts of large Gen 3 in an intentional programme as an initial decision, followed by the parallel stage-gated development of light water small modular reactors and Gen 4. But for big reactors, the decision's not when to start, but when to stop. So, realising the potential for nuclear to contribute to UK net zero, and I'm on track to finish. So, Scott, you're right for questions. So, if we look at the Energy White Paper in 2007, there were a large brace of NPR actions, and they're listed on the chart on the left. And since 2009, further NPR actions have been taken that are enabling frameworks to support nuclear new build, and they're listed on the right. But we know that we would expect that the Committee on Climate Change is going to advise later in the year on the next carbon, on a later carbon budget, I think the 6th carbon budget, but the UK is not currently on track for net zero. Now, those of you that have been in the sector for as long as me might recognise this particular chart, which is known within the industry as Vincent de Rivaz' Christmas turkey dinner chart, in that the timeline in 2009 was a projection that by 2017 EDF employees could eat their Christmas dinner off an electric oven using electricity generated by Hinkley Point C. And clearly that's not how things turned out. And at 2009, the first nuclear power station was expected to be 8 years away at 2017. And at 2020, operation of the first nuclear power station is now within 5 years at 2025. But that means by 2025, it will have taken 18 years to bring 3.3 gigawatts of new nuclear capacity into operation. And this rate of progress is simply too slow for a significant nuclear contribution to net zero. And there are other places in the world that have started from a poorer start position and have made much more progress in the same time. So my message is the policy, may be right and may be the same, but the policy framework to deliver it must change. And so really that's my last key message. Hinkley Point is progressing, and take my hat off to EDF for that. But nuclear is not on track for making a significant contribution to net zero in 2050. And if nuclear is to make such a contribution, then the policy framework must change. Now, I said I'd speak for 35 minutes. I think my time is up. These are my key messages and my concluding slide, but I would expect that you would recognise these as I've sorted them through the deck as we've gone. So I won't speak into detail to these again. At that point, I'll conclude my presentation and pass over to Scott Milne.
Mike, thank you so much. Looking at the Q&A, we have a really healthy list of questions that have come through, so thank you to everyone that's posted. If I start right up at the top, just a clarification question from Joe. Will a recording of the session be available? Yes, it will, Joe. Thanks for that. We'll be posting something around this afternoon with a link to the recording. Thanks for that. David Orr, why only Gen 4 for hydrogen production? Stations today can produce using electrolysis, as can all the options. There's a kind of modelling question in there as well, Mike, which I'll just kind of chip in, I guess, that it's entirely possible, in fact, for the ESME model to represent a mix with Gen 3 as part of the electricity mix plus electrolysis capacity, and you could then interpret that as being co-located, although the model itself doesn't do kind of site-specific co-locations. So that's the kind of modelling response to that question. Mike, I don't know if you have anything to add.
So I would, and David, it's a great question. What we're really trying to do is look for things of no regret and do it in a transparent modelling approach. And so, you know, I've been consistent for things like district heat in that although we've modelled it for light water small modular reactors, you know, all nuclear technologies can do this. And in the same way, on the same site, all nuclear technologies can generate hydrogen co-located on the same site through a range of technologies. So I haven't dismissed it, but there are a limit to the number of modelling permutations that we can set up, digest and present in a transparent manner. So we're very clearly not saying that light water small modular reactors are not suitable for hydrogen production. It's just that that's a particular combination that we've not modelled in this set of scenarios. And it just brings me back to the point that I mentioned at the start of we're looking for things that seem to be low or no regret, and we're not presenting a system blueprint for 2050.
Thank you, Mike. And the next question is from Tom Stewart, and it's related. The Gen 4 nuclear cogeneration with hydrogen model, is this the nuclear plant itself being flexible, or is this just, in effect, moving output from grid output to a private wire electrolyser?
So the way that we've set up the Generation 4 technology is we've used some referenced concept designs published by JAEA. So we're not saying in the model it has to be a high temperature gas technology, but I've used technologies where I have referenceable sources, and we've combined that with referenceable cost estimates for the JAEA technology, and then increase those cost estimates for a number of reasons. So we've driven the costs up. Now, JAEA are developing a thermochemical approach to the production of nuclear, but in our ESME approach, we've assumed a cost envelope for a hydrogen production technology. We've not delivered a certainty over which particular hydrogen production technology that is. So there are developing options from, you know, low temperature electrolysis is available today. There's a recent nuclear lab report from America about higher temperature options and higher temperature steam electrolysis that can be delivered with light water reactors. And there are a number of thermochemical cycles for the direct use of heat to produce hydrogen that require some electricity, but it's not the dominant vector in the hydrogen production.
Thanks, Mike. And brief question here, which I'll take from Mike Case. Are interconnectors assumed to be carbon zero? If so, why? Very, very briefly, the treatment of interconnectors in these models is always fraught with difficulty and risk and uncertainty as to what's on the other end of the wire. And for that reason, we've assumed no net imports from interconnectors in the ESME model. So it forces it to build a more kind of self-sufficient energy system in the UK than may be necessary, but that's our kind of basis for the modelling work. Next question, anonymous here, but it's a strong conclusion to say that net zero is possible without nuclear. Do you think it is if you only had CCS capture rates at 90 or 95%? And how do you consider upstream greenhouse gas emissions associated with gas CCS from extracting and transporting gas, either long distance pipeline or LNG?
So I think I'm briefly going to turn my camera off just to make sure that the if it helps maintain the audio quality. So forgive me for a moment. I think at this stage, making an assumption that you can deliver net zero without nuclear is brave, because it's making an assumption of a lot of technologies having to deliver what is being assumed as their promise. And there's a whole raft of things in there to get from, 90% to 100%, from a level of reforestation through very high levels of biomass with carbon capture and storage to deliver negative credits. And carbon capture and storage deployment is taking place around the world at the moment. So I'm not in the camp of deniers that says that's not an important technology for the UK, but assuming that it can deliver at 90% rate and with all technologies, may be a brave assumption until it's proven. And therefore, a world with no nuclear depends on a vast quantity of renewables. It's would be a higher cost solution than otherwise would be available if nuclear gets its act together and delivers the cost reductions which are eminently achievable. And also there is an issue over landscape use, that to deliver the amount of energy that we need for net zero and deliver the energy intensity, this quantity of renewables, we would have to accept the landscape and visual impact changes that would come with that. So I think at this stage it's a brave assumption that you can do net zero with no new nuclear.
Thanks, Mike. So I'll just say it's looking pretty clear that I won't get through all 31 of the questions that have been posted, and there are more coming in. Again, thanks for those. If we don't get to your question, look out for the email we'll send probably tomorrow afternoon once Mike's had a chance to get through and respond to those. So we will get round to them if we don't cover them today. So on that basis, I'm just going to pick out some highlights then. So Anonymous, do you feel SMRs feeding district heat will be widely acceptable to the public, given the required proximity of nuclear plant to large settlements? And how is public sentiment considered in these results?
So we've done some further work, which isn't reported here, but it speaks to exactly that point. And public acceptance is a key part of technology development and commercialization, and then therefore public support is really important. And I think a more realistic approach to nuclear deployment is fewer sites with higher deployment levels per site in areas and regions where communities want that technology because of the economic benefits it can bring to either replace retiring nuclear power stations or bring new jobs and economic prosperity to regions where, with the transition to net zero, some existing industries will diminish. So in future work, which we're not ready to publish and not in a position to do so at the moment, but we're certainly not saying scattering light water small modular reactors around the country to feed district heating energy systems. I think a more credible approach is the plants we need to be where they need to be because of the economic benefits and the acceptance of local communities. And if that gives opportunities to connect to district heating systems, then that makes sense. But I'm not advocating a policy of their wide distribution around the country, because I think public opinion would need to be ready for that. And public opinion is very, very important.
Thank you, Mike. From Dave Cole, very quickly, I can take this. Are the build rates required to create the amount of infrastructure required by a certain time and getting to 2050 considered in the model? Yes, so all the technologies and underlying infrastructure, they have build rate constraints, meaning you would have to start early in order to get to a given point if you're maxing out the build rates over time. Also, for certain technologies, like some of the advanced technologies Mike has described today, there are also data first deployment constraints, meaning they can't be deployed until a given year. And again, from that point, a given rate cap. I'll skip a few if I could, and apologies if that includes yours. We need a fusion question, of course. So from Lewis, with some private fusion systems likely to be fully operating by early 2030, how does the potential for baseload fusion factor into your calculations?
So, great question. And we don't model explicitly fusion technology within our brace of nuclear technologies within ESME at the moment. But I think there are some really interesting indications that there is a really important role for low cost, high temperature heat. And in a way, we've modeled that through what we've represented in the Generation 4 variant. But in essence, what that technology does is deliver high temperature heat with a given cost profile. And that could be used as a proxy for fusion plants, which again can deliver high temperature heat with a cost profile. And I think what's emerging, and I hinted at it earlier, there's a sensitivity analysis which says, you know, if you can get the cost to the right place, high temperature heat for the production of hydrogen can be a really important market, because it starts to not just supply the hydrogen economy, but drive the hydrogen economy. As the costs come down, it becomes more attractive as a vector of choice. And with really low cost of hydrogen, you're into potential for a replacement for natural gas, in a widespread distribution network. And with really low cost hydrogen, you can start to think about the possibility of liquid synthetic fuels for decarbonising aviation. So, I think the study doesn't explicitly speak to fusion, but I think there are some great learning points for fusion from this work.
Great, thanks, Mike. And there was a question later on the synthetic fuels production. Perhaps that's covered it, but to that person, we'll come back to you. From Eugene Schwaberhaus, Mike, what has your model assumed about the date Gen 4 becomes available and how fast they can be introduced, displacing or adding to existing capacity? And does the model have to wait for existing capacity to retire to introduce new ones, or is it forced to do so?
So the model doesn't wait for new capacity to retire. The model is, forgive me, Scott, I'm going to use the word, the model is hungry for dispatchable power generation, through the transition period. And so you don't need to wait for existing nuclear plants to retire. In this work, we've assumed that there's a commercial generation 4 plant that can commence operations from 2035, which some say is pretty racy. And I have other colleagues which say, well, that's too slow. You can do it more quickly than that. I think the speed of introduction of Gen 4 is really strongly influenced by how you choose to approach it. I think if there are opportunities for international collaboration, particularly with designs that have designs for commercial plant that have already been broadly exposed to a national regulator, there's a route for accelerating that commercialisation. So the choices that are made in the route to commercialisation can affect what that deployment date is. The base assumption in this model that we've used in the work I've shown you today is that commercial operations from 2035.
Mike, I'll squeeze in one final question then. It's a good one to end on, from Mike Lewis. Great work, and where do you see and want to take the work next?
I think the first thing I need to do is with colleagues listen to what people tell us about this work. There's a whole range of stakeholders, but I think within the paper there are a few things. I've stressed that ESME is not a market model and it's not a system blueprint. There's a role for multi-vector market models to inform deployment decisions that can also acknowledge the trajectory of plants in their transition from folk to oak. So that's one area that needs to be explored. I think there was also a recent NIRAB report published, annual report, giving advice to government on nuclear innovation. I think that's important. And also, I don't think we've reached the floor for costs for nuclear. I think what we're learning from other industries are their particular delivery approaches which can be used to drive down cost. And I think there is more that can be done to reduce costs even further and potentially access this very low cost hydrogen option and how that might step forward into synthetic fuels. So I think the key thing is listen, understand what our stakeholders tell us, but I think there are a range of things that could and should be done next.
Maggie, thank you very much. That's 11 o'clock, so we're going to have to leave it there. Thanks to all of you for joining us. Once again, we'll be circulating an email with the recording of this session this afternoon, and we will be looking to answer as many of these questions as possible and circulate that again to all of you, hopefully by close of play tomorrow. So once again, thank you very much for joining us. And finally, thanks again to Mike Middleton for an interesting presentation. Thank you.